We've talked about two optimization algorithms, gradient descent and Newton's method for optimizing the objective we define for logistic regression. In this video, we'll discuss some properties of each of these two methods and try to figure out when one of these methods may be preferable rather than the other. Let's start by talking about some of the properties of gradient descent and of logistic regression. Let's write them down here. Newton's method. So, one first difference, and this may be a minor one, and maybe a slightly questionable one, is that gradient descent may be simpler to implement, and logistic regression, and Newton's method might be slightly more complex. And and the reason I say that is because gradient descent doesn't require a matrix inversion, for instance, and so it really depends on what tools you have and how you're doing this. But if using gradient descent lets you more simply and more quickly get something running, so you have something to test and iterate and improve on, then sometimes that may be preferable. And I'll actually say more later about this idea of trying to get something quickly running so you can improve on it. On the flip side of this equation is that gradient descent needs a choice of the learning rate alpha, whereas Newton's method has no parameters that you need to set. And so this actually maybe sometimes flips the advantage the other way. In particular, depending on how much time you end up spent needing to tune the learning rate alpha, again, now it's maybe slightly more questionable whether gradient descent or Newton's method would be a quicker maybe a quicker algorithm to get running. I actually tend to think gradient descent, despite having the set alpha, is often maybe a slightly simpler and quicker algorithm to get running, but this is certainly highly debatable, and depending on your problem and other details, the advantage may well go to Newton's method instead. So far, maybe it seems a wash between the two algorithms, or maybe small differences. Here's a more significant difference, which is gradient descent, it turns out, needs more iterations. Right, so you may need to run a lot of iterations of gradient descent before it converges, and maybe you may need hundreds or thousands or tens of thousands of iterations or more, and this depends a lot on your problem. Whereas Newton's method typically needs fewer iterations. And in particular, as I was saying in the previous video, depending on the problem, is not atypical to see conversions in like maybe 5, 15 iterations, or not much more than that. However, even though gradient descent needs more iterations to converge, it turns out each iteration is cheap. And each iteration costs O of n, where n is the number of features. Okay? There's actually O of m times n, where m is the training set size, but I'm going to ignore m now and just focus on the effect on the number of features. In contrast, for Newton's method, each iteration is more expensive, is relatively more expensive. And in particular, you need to take the Hessian matrix, which is a n plus 1 by n plus 1 matrix, and you need to compute the inverse, right? So, the cost of inverting a matrix is, let's say, roughly O of n cubed. It's not really, but it's close enough. And so the cost per iteration of Newton's method is therefore higher. And so, if n is small, we'll say exactly what small means. So when n is small, when you have a small number of features, then the cost per iteration won't be too much, and Newton's method may be preferable. And when n is large, then the cost per iteration of gradient descent would be much cheaper, and then gradient descent may be preferable. Concretely, what do small and large mean? Well, concretely, if n is less than 1,000, say, this is what I call small, or this is a small number of features, then, for Newton's method, you need to invert like 1,000 by 1,000 or 1,001 by 1,001 matrix. But on modern computers, using modern numerical linear algebra libraries, this is, it's pretty easy to invert, right? So inverting 1,000 by 1,000 matrix these days is really not a big deal. If you're using MATLAB or Octave, just use the built-in libraries. If you're using C++, Java, or NumPy, then if you're using C++ or NumPy, then definitely do use a good numerical linear algebra library to compute this inverse. We're using Python, NumPy, or the modern numerical linear algebra libraries, we have no problem inverting 1,000 by 1,000 matrix. So, if this is the case, Newton's method will be just fine. If n is, so stepping up one order of magnitude, so if n is around, say, 10,000, then Newton's method would still be doable, but I would seriously hesitate. I would seriously pause and think about it. So in particular, if you have a 10,000 by 10,000 matrix, inverting it on a modern computer, that's going to be a bit slow. So this is maybe beyond the point where I would still be comfortable using Newton's method. And if with this size problem, I would think about it. You could probably get Newton's to work, but I would probably be inclined to use gradient descent instead. And finally, if n is much larger, if n is, say, let's say 50,000 or 100,000, right? If you have, or even larger, so if you have like 50,000 features, then I would almost certainly use gradient descent. Okay, and in particular, even on a modern computer, 100,000 by 100,000 matrix. Well, even on a modern computer, storing such a big matrix in computer memory and trying to invert that would be very challenging. And so just to wrap up and summarize, right? If the number of features is, the order of 1,000 or smaller, gradient descent, Newton's method should work just fine. If the number of features is like 50,000 or higher, or maybe even 10,000 or higher, I would lean towards using gradient descent. But somewhere in between, it's ambiguous, and maybe one algorithm will be preferable than the other. And with that, well, at least these are the rules of thumb that I use for whether or not to use Newton's method, and what it really boils down to is whether you can invert the Hessian efficiently. And hopefully these rules of thumb will help you to choose between Newton's method and gradient descent for your problems. But of course, because of ease of implementation, even if you have a small set of features, if you choose to use gradient descent because it's easier and quicker to get running, that's perfectly fine too, and I also do that sometimes.